what we've done is we have, in Chapter 2, kind of talked about a few key concepts for functions, okay? And we've kind of looked at collectively all types of functions. We talked about absolute value functions. We talked about piecewise functions. We talked about sometimes quadratic, sometimes cubic. But we tried to learn concepts like one-to-one ideas, inverse ideas, that type of stuff. Now in this chapter, what we're going to do is we're going to go back and kind of pick off certain types of functions and dive into those individual functions a little bit more. And the first one I guess Chapter 3 is going to talk about essentially two types of functions: polynomial functions and rational functions. Polynomial and rational. First, start talking about polynomial, because rationals are actually the division of two polynomial functions. So we're talking about polynomial functions, and the most simplistic polynomial functions that we can deal with are constant functions and linear functions, which are kind of boring. We've talked about those. You know, that's like all of Algebra 1. We're going to start with quadratic functions today. That's the first polynomial function we'll deal with. You guys know a lot about quadratic functions already. They're your parabolas, right? They're your x squared things, okay? So some of this might seem as review, but some of it is important to review, and also at the same time it's important to talk about because it might not be review, okay? Maybe you've never interpreted it this way or made these connections, these links that we're going to learn. That's what the math is, guys, the relationships, right? And being able to decide and understand those relationships and when to use them. But here's the polynomial function, a function that is defined by what we call a polynomial expression. That is a polynomial expression down there. In a minute, if I kind of delete that out, okay, because with it's an equation. This is the polynomial expression that we talked about earlier in the year. Okay, we'll make it a polynomial function. We make it an equation. Okay, and we're making the argument that this is a function. So fast and vertical line text. Okay, whether it has inverses and all that kind of stuff would be something we have to decide eventually, okay, and determine algebraically. But we've seen that, and then you remember the a sub n stuff. Those are just referring to our coefficients. The x to the n, okay, that's talking about my exponent, okay. We want n to be a integer, a positive integer, or it's not polynomial. We talked about that before. A sub n cannot be 0 because then that first term would go away. But our exponents are decreasing all the way down to 0. Okay, so if I start with n being 7, I'd have this a sixth term, a fifth term, a fourth term, a third term, a second term, a first term, and a 0 term. Does that make sense? Now, some of those might not be represented because their coefficients might be 0, and that term actually dissolves, but it's still really there. So I can write 0 times x to like the fourth if I needed to. Okay. This says we've already talked about degree 0 and degree 1. Degree 0 again would look like this, meaning that thing right there went to a 0, and x to 0 is just 1. So all you're left with is this constant, and if all you're left with is that constant, then you have what we call a constant function, which is the horizontal line, right? We've also dealt with n being 1. Okay, so you have this coefficient out here, which is your slope, and then you have this constant here, which we've kind of analyzed as our y-intercept for linear functions, right? So those we've talked about. The ones we want to talk about in a little bit more detail today are our quadratic functions. And again, I don't think you probably need to write this down, because if you don't know if that's a quadratic function, you've probably been asleep for 3 years. Okay? F of x equals ax squared plus bx plus c. A cannot be 0. If a is 0, what do you get? You get a linear function. Okay, so it would be a potential issue if we let a be 0. And that's the thing about definitions, guys. When we write a definition, that's what we got right here. We have to write that so nothing accidentally gets classified as that object, but really isn't that object, right? So if I leave out that aspect that a cannot be 0, I accidentally, without knowing, allow all my linear functions to be considered quadratic. Does that make sense? And that's a problem. We know they're different. So we've got to make sure that we have that component that a does not equal 0. Call it the degree 2 polynomial. if you don't want to use the word quadratic. All right. Here's what I don't like. If you were to do like a Google search for standard form of quadratic function, some returns are going to be ax squared plus bx plus c. Okay, that's standard form, which is what I agree with. Others are going to tell you, like this textbook does, and like WebAssign does, and what the author of OpenStax, which is the textbook that Rose uses to kind of govern the class, are going to say it's this bottom one, f of x equals a times quantity x minus a squared plus k is standard form. Okay, I prefer to call that one the vertex form. Okay, because it tells you when you look at it what the vertex of your parabola is. Okay, so here's the thing: you guys know that some texts, if I gave you 20 textbooks, I think 10 of them probably say call that standard form, 10 of them probably call it vertex form. Okay, I believe Miss Coles last year would call it vertex form. Okay. The way I was taught, because I was taught by her. So when we see this, and the terminology may be different, okay? There's really only there's two ways you can see it. All right. So if they give you this one, and they ask you turn it into standard form, does it kind of shed light that if I'm going to turn it into something, then I got to go to the other option, which would be this. Does that make sense? Okay. Or if they start with this. So if they say this is standard form, turn it into vertex form, and be this. Okay. But if they are saying this is standard form, I don't know what wording they would use here, because there really isn't another wording here. And they say turn it into maybe polynomial form, then it would be that. Does that make sense? You really only got two routes you can go. So whatever they give you, if they ask you to transform it, you go to the other version. Okay? I think hopefully that's kind of obvious. But what happens here, and the way we go from these two things, obviously from this one, and I'm going to call that vertex form. We go from vertex form to polynomial form, or what I like to call standard form. To do that route, all you have to do is your algebra. All right? You expand that. You take x minus a squared, expand that, multiply your a through, and then you add k to it. And that should get me back to ax squared plus bx plus c. Now, if I were to do that in those versions, because we're going to get some ugly things for a, b, and c. Okay? Maybe we'll talk about that tomorrow. But if I wanted to go from this version to that version, we have to complete the square. And that's what you see there. It says by completing the square is how we do that switch of versions. But when we're in that bottom version, it should tell you what the vertex is. Okay? Because think about this. A, so the parent function here is x squared, right? Would everybody agree with that? Okay? When I subtract something from x, and in this case I'm subtracting h, before I square it, before I do any operations to it, I'm changing that x through subtraction. How is that going to transform, or how is that going to move my parabola x squared? It moves, so normally my parabola would be right there, that's x squared, right? It's going to move it to the right 8 units. Okay? So that's kind of nice. So at this point, 0, 0, which is like my vertex of my parent function, gets moved here. But what's that k going to do? Move it up. So does that take 0, 0, which was my vertex of x squared, and put my vertex now at h comma k? Does that make sense to everybody? So what's nice about that is when I look at this, that number and that number as an ordered pair tell me my vertex. Okay. Now here's even a better, or I don't say better, but more information, is that when I look at the a value and it's positive, and that's what they're saying here in this version right there. When a is positive, okay, it's obviously a stretch. Okay, it's going to change my y values. But if it's positive, your y values stay positive. Does that make sense? Okay. When it's, I guess I don't want to say your a values stay positive, but it's a positive multiplier, and that's going to force this thing to be concave up. Okay, you guys remember hearing that word or that phrase? Okay, concave up is the idea if I pour water into this parabola, it's going to hold that water. Okay, and that's because A is positive. Now, if A was negative, that's what they're saying here. Okay, now you don't see the negative sign, but right here they tell you A is negative, right? Okay. Think about what that does. We said a negative out front is an x-axis reflection, right? Okay, so that's what's going on here. If I reflect this thing here across the x-axis, okay, before I do the vertical shift, I'm going to get this thing right here. But what is nice about that, if A is positive, we should know that this vertex is a minimum, right? And here, if A is negative, we should know this vertex is a maximum. And so if I know those are minimums and maximums respectively, I should know then on the interval in which this thing is decreasing over here, in which it's increasing there. And over here, it kind of flips. Now it's increasing to decreasing. Does that make sense? So I should be able to, and we'll practice this, but we should be able to interpret all of that from just looking at that algebraic phrase, okay? And not having to graph anything if we don't want to. Okay? I think graphing after we interpret and try to pull all the information out is a good idea to make sure that we can validate that information. Now I'll do an example with you. All right, so when we see this, okay, and I'm going to eliminate some of this stuff and give myself a little bit of room. All right, so express f in standard form. So right now, and I'm just using terminology textbook uses. Right now, they're saying that's not standard form. So then we might change it so that we can see our transformations, right? Before we do that, because the argument is, well, then why do they ever deal with this? Why do they ever give this to me in this format if it's not really useful? Yeah, it is useful. Think about this. If I had f of x equals 2x plus 3, I'll just say 2x plus 13. What is that number right there for your line, 2x plus 13? Y-intercept, right? And it's a y-intercept because x is what value? Yeah, when x is 0, right, f of 0 equals 2 times 0 plus 13, what are you left with? 13. So the x value was 0, the y value, the return value is 13, right? So we recognize that that's going to be the case every single time, and we just say, okay, well, that, we call it b in Algebra 1, right? That b term is always your y-intercept. Well, is there anything different about y-intercepts when we're talking about a parabola or a cubic or a quartic or a quintic? Any polynomial or not? X is still 0, right, for every y-intercept? So if x is 0, what happens to this thing? Yeah, it goes away, it goes to 0. What happens to this one? It goes to 0. Anything that has an x with it is going to go to 0. What are you left with? Just 13. So in that form, the constant value, okay, in this case the 13, tells me my y-intercept. That's not something that's obvious when we deal with the vertex form, or what they're called standard form. So this is how we do it, okay? You've done it before. You've done this in the 9th grade. You did it with me in geometry a couple times. Okay, you did it in Algebra 2. And then we did it earlier this year. Get this thing into what we call standard form with square. Okay? To complete a square, first thing you're going to do is divide everything by your A coefficient. Everything. So f of x is part of everything. Your y value. So we're going to divide that by 2. Divide 2x squared by 2. Divide 12x by 2. Divide 13 by 2. Okay? First step, divide everything by your A coefficient. Second step, move your, which is now kind of our, it's still our C term, but now it's C over A. We're going to move that to the other side. And these two steps, guys, they're independent of one another. The division of 2 and the removal of C. Meaning you can do them in any order, or you can do them together at the same time. Okay? Whichever one you prefer. The better you get at it, I think most of you probably prefer and realize that doing it at the same time is not that difficult. The next step is to take our B term now, which is the coefficient for x, and we take half of it, and we square that. Yeah, add that on here. If I add 9 to the left or right hand side, I add 9 to the left hand side, right? Now the reason we do that, that is going to develop for us what we call a perfect trinomial, and we're going to rewrite this as x minus 3 squared. You remember, that thing right there is always, that term is always half of your b term. It's what you took before you squared things. Okay? Now that right there, that's, if I think about the a times x minus h squared plus k version, that's the x minus h squared part. Okay? I still need the a and I still need the k, and that's where they come into the play here in the next step. Right here, I still got to do this algebra here. Is my 18 half? Okay, so I'm going to have actually f of x over 2, plus 5 halves. We're going to add those two things together. What am I going to do with that 5 halves? Subtract it, so I get f of x over 2 is equal to now x minus 3 squared minus 5 halves. Now, that is not the parabola that we're looking for because that's half of what we started with. So what do I need to do with this 2? Multiply that 2 back to it. Okay? And that's always going to be, you know, if that number was a 3 or 4 or 5, we multiply by 3 or 4 or 5. Okay. We get f of x. Okay. Now here, these are two objects, and this is what people get confused with. I think if I'm multiplying both sides by 2, I'm really doing this. Object number 1 multiplied by 2. Object number 2 multiplied by 2. If you distribute that correctly, you get this. Minus 5. Telling me then 3, negative 5 is my vertex because of this transformation. We'll pick up with that tomorrow, and I'll get those tests graded as soon as I possibly can. I got dance tonight, got trick or treat tomorrow, piano lessons tomorrow. I don't know if I'll be doing a lot of this work at home or not.